is zeros of polynomial functions continued. Last time we talked about zeros of polynomial functions and we were finding the real zeros. This time we're going to be finding the complex zeros of the polynomial functions. That's what this lesson is about. So this is still 2.4 from your book. So complex zeros, we're going to talk about a couple theorems before we get too into this. So a polynomial function of degree n has exactly n zeros. We said before it had at most n zeros. That was at most n real zeros. A polynomial function of degree n has exactly n zeros when you're including repeated zeros in the complex number system. Now we're talking about complex zeros. So you can have at most n real zeros, but you definitely for a polynomial function have exactly n zeros. So a polynomial function of degree n, where n is greater than 0, has at least 1 0 in the complex number system. So we're definitely going to have at least 1 0 that's complex for any polynomial of degree n, where n is greater than 0. So that's the fundamental theorem of algebra. Let's look at the linear factorization theorem. So if f of x is a polynomial of degree n greater than 0, the f has exactly n linear factors. What are linear factors? That's this x minus c1, x minus c2. So for f of x equals, we're saying a polynomial of degree n greater than 0, the f has exactly n linear factors. So we're going to end up with an equation that is some constant, a sub n, times x minus c1, that's your first linear factor, x minus c2, that's your second linear factor, multiplied by ... all the way until x minus c sub n. So that last term is your nth linear factor. A sub n is just some real non-zero number, and c1, c2, all the way to cn, those are your complex zeros, including repeated zeros of f. Okay, so we have n linear factors. That's going to include, for c1, c2, cn, complex zeros, and including repeated zeros of f. So the conjugate root theorem says that whenever one root occurs at a plus bi, whenever we have one root at a plus bi, then we were also going to have the complex conjugate What's the complex conjugate of a plus bi is a minus bi. That's also going to be a root. So anytime you have one root at a plus bi, the complex conjugate, a minus bi, is also a root. Okay, let's look at an example. So write a polynomial of least degree with real coefficients in standard form that has -2, 4, and 3 minus I as zeros. So our zeros are -2, 4, and 3 minus I. So first thing we know from that conjugate root theorem is that if 3 minus I is a 0, then we also have a 0 at 3 plus I. We definitely have a 0 at the complex conjugate. So now all we're doing is filling that in. We start with x minus a 0, x minus a 0, x minus a 0. We have all of these in parentheses multiplied together. So let's plug in our zeros. We knew we had -2, we have positive 4, we have 3 minus I, and we have 3 plus I. And out here at the front we have a sub n, if you remember. A sub n can be any real number, but it's easiest to make a sub n equal to 1. So we're just going to put a big 1 out there because it doesn't affect anything, okay? So we need to rewrite this equation now to simplify because we had some x minus and -2, for example. And so that becomes 1, our a sub n, times x plus 2, parentheses x minus 4, parentheses x minus 3 minus I, parentheses x minus 3 plus I. So what you know about this is the 3 minus I and the 3 plus I, we're going to have some canceling out in that situation, right? We end up with x squared minus 6x plus 10, and then those first terms multiplied together, we get x squared minus 2x minus 8. We can now multiply these together, and we end up with x to the 4th minus 8x cubed plus 14x squared plus 28x minus 80. So that's, you know, just by given, negative 2, 4, and 3 minus I as your zeros, that this is your f of x. And any multiples of this would also be f of x. So if we multiply this whole thing by 2, that would also work to find those zeros. Okay, so let's move on by factoring polynomials over the real. Every polynomial function of degree n greater than 1, n greater than 0, so we're dealing with x squared or x cubed. We're not dealing with x to the negative 1. So every polynomial function of degree n greater than 0, and that has to be your highest degree, with real coefficients can be written as the product of linear factors and irreducible quadratic factors, each with real coefficients. What is an irreducible quadratic factor? So an irreducible quadratic factor is something like x squared plus 1. That's a quadratic equation, but that is the simplest form. That is the most reduced form. So that is an irreducible quadratic factor. Okay, so let's look at an example. Given k of x equals x to the 5th minus 18x cubed plus 30x squared minus 19x plus 30, write k of x as the product of linear and irreducible quadratic factors. So we're going to put a bunch of the stuff that we learned all together right here. So the possible real zeros include factors of 30. Remember that from last time? Our leading coefficient is 1, so all we care about is that 30 in order to look at our real zeros. So if we break down what are the factors of 30, we get plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 5, plus or minus 6, plus or minus 10, plus or minus 15, and plus or minus 30. Now we're going to look at the original polynomial's sign variations, right? How many times are we changing sign? So we go from a positive 8x fifth to a negative 18x cubed, then back to a positive 30x squared, to a negative 19x, to a positive 30. So our number of sign variations that we have is 4. We have 1, 2, 3, 4 sign variations, which means that we can have either 4, 2, or 0 positive real zeros. So again, we have to subtract that 2 in order to figure out how many zeros could we have that are positive. That's what we're doing when we're looking at the k of x and the sign variations. But we also need to evaluate the sign variations of k of negative x. Right? That's going to give us our negative real zeros. So far we've sort of started to find our positive real zeros. Now we need to find our negative real zeros. We determine how many. So we plug in a negative x into our k of x, and we're going to evaluate how many sign variations we have for this. So we move from negative to positive, and then that's it. We don't have any more sign variations. So k of negative x has only one sign variation. Therefore, k of x has either 4, 2, or 0 positive real zeros, and 1, for sure, 1 negative real zero. So we can graph this to find out where we think that these zeros might occur. And it appears we have one at x equals negative 5. So we're looking at the options from our factors as our possible options. So it looks like we might have one at x equals negative 5. So in order to test this, again, we're going to use synthetic division. We want to see if we have a 0, so we want to get f of negative 5 equals 0. We want our remainder to be 0. So we do the synthetic division for negative 5 with that original polynomial. Don't forget to fill in your zeros wherever you had zeros. And we end up with 0 as our answer. We can go through all that synthetic division if you feel comfortable, but again, you're dropping down that 1, you're multiplying your 1 by negative 5, you're moving that negative 5 up, and you're adding it to your 0, then you're multiplying negative 5 by whatever that result is. So you have negative 5 times negative 5, you get positive 25, then you're adding negative 18, and positive 25, you get positive 7, and so on and so on. You end up with a 0. So we're testing a negative 5. That's our one negative 0. We knew we were only going to have one. That's it. So any other real zeros are going to be positive. So the graph appears to show from the factors above that 2 and 3 might also be other rational zeros. But again, we need to test that with synthetic division. So we plug in 2 for synthetic division, we get a remainder of 0. We plug in 3 for synthetic division, we get a remainder of 0, which means that both 2 and 3 are positive real zeros. But we have a remaining quadratic factor, right? Because what did we start with? We found all of those zeros, but we started with an x to the 5th. So we need our remaining quadratic factor, which is x squared plus 1, that's going to yield no real zeros. That doesn't create any real zeros, right? Because if we try to set that equal to 0, we have x squared equals negative 1, right? We know that there has to be an I in that equation. So that, therefore, this we call irreducible over the reals, which is just a fancy way of saying that that last factor doesn't have any real zeros. So let's plug that in. We then have our factors as x plus 5 times x minus 2 times x minus 3. We're plugging in all our zeros times x squared plus 1. So that is what we're going to get. We can also rewrite this as a product of linear factors, including those irrational zeros. So we solve, we have x squared plus 1 equals 0. That's the same as x squared minus a square root of negative 1 squared, or x squared minus I squared, which is the same as x plus I times x minus I. So if you didn't want to write that as x plus 5 times x minus 2 times x minus 3 times x squared plus 1, you could change that x squared plus 1 to x plus I and x minus I. So therefore, our zeros are, we found all of our zeros. They're going to be at negative 5, positive 2, positive 3, negative 1, negative I, and positive I. Those are your zeros.